All right, everyone. So this is chapter 15, the last chapter of our class. So this is on fluids and elasticity. So in this chapter, we're going to be exploring, um, you can see, right, the macroscopic system that flow or deform. So we're going to identify what is a fluid, and what are the applications of fluid, and then we can look at some system, right? So let's say the solid, let's say material that can uh, let's say deform or change the shape when under some kind of stress or strain. All right, so one of the things we're going to talk about in this chapter is that the matter can be in three different states. So it can be in solid, liquid, or gas. So we're going to talk about, let's say, in terms of which of these states can be considered as a fluid, and how then we can, uh, let's say, separate something that is a fluid from something that is not a fluid. Right, so we start with gas. So you can say, right, the gas in a system in which each molecule moves through space as a free particle until on occasion it collides with another molecule or with the wall of the container. That means when we talk about solid, liquid, or gas, we are in a way talking about how the molecules are structured. So in a solid state, the molecules are generally very close to one another, and there's this, um, molecular intermolecular forces keeping them together. So for example, let's say think like the ice cube, right? So the those forces can keep all the molecules together, which allows them, the ice cube to keep its shape and to keep its volume. So but when we talk about, for example, a gas, then the force, those those sort of like, let's say, intermolecular forces that keep the molecules together, in a solid, so they're pretty much not present at all. That means, those molecules are moving so fast, and that they basically break away from, each other, in terms of those, break away from those forces, and can freely move, let's say, in a container. That means there is no definite shape, no definite volume, right? So they can just basically randomly move. And generally what they do, they, collide with each other. And as they collide with each other and collide with the, let's say, container wall, we're going to see, right, they exert force on that wall. And that force on the wall, which later on we're going to be able to then define as pressure. But right now, one thing we can see here, that, they can technically flow, right? They can move freely, you know and that what, allows us to call gas, basically, or identify gas as a fluid. Okay, so gases are fluids because they can flow. So they flow and exert pressure. All right, so we can compress gas, and we can also change the volume, right, freely, for example, by compressing, or let's say, or also expanding our system. So that means they're easily compressible. And then we can look at a liquid. So with the liquids, those intermolecular forces are a little bit stronger. They're able to keep them a little bit closer together, but it's not strong enough to allow them to move around each other, and basically break away that shape that they, let's say, have when it's in their solid state. So, but they can have a volume, right? So let's say, not necessarily like, let's say, um, like a shape, but they can keep the volume. They can take the, shape of a container, right? They're in, and one thing you can see, right? They have a well-defined surface, and they also can flow. That means liquids are also fluids, so they can flow and they can exert pressure. That means those molecules in the wall, right? They are actually constantly moving, and they colliding with each other and with the container wall. The difference between gas and a liquid is that liquid, is incompressible. So you can't really compress it. So the volume of a liquid is not easily increased or decreased. So that's, in a way, the main difference, even though one of the things we can talk about here, that kind of like, let's say, same for both gas and liquid, is that they can flow. And then the, combination of a liquid and a gas, can be put in, sort of like a specific category that we can call fluids. All right, so a solid, that means cannot be called a fluid because it cannot flow and cannot exert pressure. But for example, here we're going to talk about then gas liquid combination as fluids. And we will look at in terms of what we mean by exerting pressure, what do we mean by flowing, and what are the applications of, let's say, fluid dynamics. One very important thing about, let's say, in this chapter that we're going to kind of have to review is to know, how to find volume, how to define volume in SI units, and basically also, let's say, density. So because one of the important things we have here is this equation where density is equals to mass over volume. This is going to be a very important equation in this chapter. So then we want to be able to, let's say, correctly calculate the density of an object from its mass and its volume. And in this particular slide, when we're going to talk about volume. So the volume is, remember, so it's a microscopic system, and representing basically the pretty much shape of a system or shape of an object. And it can be represented in terms of cubic centimeter, liters, cubic meters, right? And for us in SI units, we want always the volume to be in cubic meters. And here are some conversion factors where 1 cubic meter is 1,000 liters, or you can say then 1 liter is, so let's say 1 liter is 10 to the negative 3 cubic meters. Okay, you can kind of like go back and forth. So or 1 liter is 1,000 cubic centimeters, and 1 cubic meter is 10 to the 6 cubic centimeters. Okay, so I always recommend, let's say, if you need to find the volume, convert everything into meters, and then use that to find the volume in meters. So for example, if you have a cube like, like this in front of you, so it's 100 centimeter by 100 centimeter by 100 centimeter. So then one of the things you can do here is do 100 times 100 times 100, then you get 10 to the 6. Okay, so 10 to the 6 is cubic centimeters, which now we know then it's 1 cubic meters. All right, so but what if it's, let's say, not, let's say a 100, right? So then you're gonna have to convert everything into, let's say, or you can calculate everything in centimeters, then convert at the end to cubic meters. But I think it's easier to just basically, since this is 100 centimeters, just 1 meter. This is again 1 meter. This is 1 meter, and then you can write one by one by one by one, right? It just gives you 1 cubic meter. So basically, it's much easier to do this calculation. Um, we also have, the mass, remember, so it has to be in kilograms whenever we get with, using it in terms of SI units. So then when you take the ratio of mass per volume, this is known as a mass density. Okay, so mass of the object in kilograms divided by the volume of the object in cubic meters gives you the density or mass density, which then can be written as kilogram per cubic meters. Okay, so that means, in this chapter we're going to be using this quite a lot, especially when we are, representing the mass. So see, if I rearrange this equation, it's mass equals density times volume. And this product of density times volume, a lot of times will be, preferred, way of writing the mass, because mass is, is equal to the product of density times volume. And a lot of times representing the mass in terms of density times volume allows us to, for example, cancel the volume, or, find the volume of an object, which is going to be, let's say, important parameter in some of the applications. All right, so the density written in kilogram per cubic meter, you can find here for some of the, let's say, more commonly used, substances. For air is 1.28 kilogram per cubic meter, which is, you can see like it's probably one of the lowest density, substances that we can have. Something that very important to know is the water, which is 1,000 kilogram per cubic meter. Seawater is slightly higher than the fresh water, but most of the time you can just use a 1,000 kilogram per cubic meter, and still get the very, very accurate value for the density. Let's say oil is 900 kilogram per cubic meters, and later on we're going to see that this becomes a important factor to to see if the oil will be floating or will be sinking when you let's say mix water and oil. um, Important, let's say the mercury is something that also can be useful, not necessarily let's say you need to memorize. So the only thing kind of like to memorize is just the uh, water. So it's 1000 kilogram per cubic meter. That means if you take one by one by one, let's say container, which is 1 cubic meter container, and fill it with with water, put it on a scale, it's going to be 1000 kilograms. All right, so mostly you can see, right, the ethyl alcohol, gasoline, let's say glycerine, those are basically kind of comparable to the water, right? Some are, have more dense, some is less dense. Most of the metals like gold, aluminum, and things like that, right? They are copper, they are much more, let's say, dense than water. Okay, so here's a little bit more complete for the solids, right? Liquids, and a little bit of gas in terms of like their densities. So you can see, right, the solids are by far the more dense, right? Because as I said, right, so molecules are very closely, let's say packed to one another. There's a force between them, just keeping their shape and volume. So their density is higher. So remember, density is just basically in terms of how much mass you have per volume, and because they are much closer packed to one another, there are more molecules per, let's say, cubic meter, so it's more dense. So let's say aluminum is something that also can be useful to know. That's about 2700 kilogram per cubic meter. And for example, gold, right, is about almost 20,000 kilograms. So it's 19.3 kilogram per cubic meter. So like let's say one of the important things to know. So you can see, right, ice, for example, is 0.917 times 10 to the 3, which means, for example, ice is less dense than water. Which means, like, let's say ice is a water in solid state, and is actually less dense than water in liquid state, which is 1000 kilogram per cubic meter. So but obviously, let's say, when you talk about steam is basically 0.598, right, in terms of kilogram per cubic meter. So it's relatively light compared to let's say fresh water. Anyway, so there's you can always refer to this table to get some of the density values. All right, so now in terms of talking about pressure. So what is pressure? How do we define pressure, and what is the basically pressure variation at, let's say, some depth or altitudes and things like that. So those are the things that we're pretty much going to be talking about the next several slides. So in terms of then what is a pressure? So think like this. So if you have a container with water, and then we make three small holes, right? So you can see, right? So let's say here's hole one, hole two, and hole three. Okay. So one of the things we want to see here is that the depth of each one. So let's say this is first one given in terms of y1, or let me like do in terms of like, let's say h1. This is in terms of surface. Here's 2, so h2. And then this one is the h3. And remember, the idea here is this. Pressure is when air molecules are moving in the container, sorry, water molecules, right? Moving in the container, and then the colliding with the container wall at, there's three positions: position one, position two, and position three. And in a way, what we can see here is that if you poke a hole, then this molecule is going to come in and then go through the hole with the same intensity like they would have if they, let's say, collided with the wall. And you can see, right, because as soon as they come out of the, that those holes, right, they, the gravity going to pull them down. So this is basically like a projectile. Okay. And the idea here is to see sort of like, let's say, which one going to come out with the larger velocity. Okay. And hopefully you guys can see that from the shape, you know, here's, let's say, velocity one, here's velocity two, and this is going to be velocity three. That means even though hole three basically coming, from a much closer to the ground hole, right? It basically reaches much greater range, or like, let's say, a larger range that, or enough that, let's say, even matches the, much higher height, which means, and or from the shape also you can see that, that means that from the hole three, the molecule actually coming with much larger velocity, which means that if it would collide with the wall instead of coming out, it would have, collided with the wall with much greater force. And that's important because one of the things we can see is that the pressure seems to be larger at greater depth. And we're going to be exploring that to see if this is true or not. Is it true that, let's say, point 0.3 going to have a higher pressure than point 0.2, and point 0.2 going to have a higher pressure than point 0.1? All right. So now to understand here is we're going to look at it in terms of a container. So where there are air molecules, water molecules in the container. Well, there are air molecules above the container, which are also important in setting up the calculations actually. But let's say we have water molecules in the container, which are, free to move around a little bit, right? Remember, so, the water molecules are actually free to move around because of the, it's a fluid. So then if we choose some area of interest like that, then we can look at in terms of when those molecules move and collide with the container wall, what they do here is they hit that, area A with some force. And then what we can do here is we can then define the pressure those water molecules exert at that area A, right, as force per unit area. So the pressure is defined as the ratio of the force to the area on which the force is exerted. Okay, that means in a way, let's say it's how much force acting on that area A due to those collisions. So then the pressure is force per area. Force is in newtons, area is in square meters. So technically it's newtons per square meters. But that's not the SI unit that we usually like to write. So we define this ratio of newtons per square meter as Pascal. Okay, so Pascal is then actual unit for the SI unit for the pressure. Okay, so technically Newton per square meter also equivalent to that. So it's also in a way in terms of the SI unit, but we also define that to be Pascal. So most of the time you can just write it Pascal instead of Newton per square meters. All right, so that means that this ratio is what we call pressure. Pressure is you apply force at some area of interest, right? Force per area, that's what we call pressure. Okay. So in a way, then this diagram kind of demonstrates sort of like, let's say, if you have thing like this, if you have some sort of like a piston with a spring attached to that, and those water molecules then bombarding this piston and basically exerting a force or a pressure on a piston, and you can see things like greater the force, more it will be compressed. So if you're able to make this device and put it in the water, and then one thing you can see here is, so this is closer to the surface, this is a little bit deeper into the surface, a depth, more depth compared to the surface, and this is basically has the greatest depth compared to the surface. And you can see, right, it is basically shows that experimentally, right, the spring is the most compressed. So that means there's actually pressure everywhere inside the container. That means water molecules is moving around and then colliding with that piston and then compressing the spring. But it seems like most of the let's say the highest or greatest force that they exert to compress it is at the greater depth. Okay, so that's kind of like one of the things that are important to understand. And also doesn't matter how this spring system, right, this device is oriented, there's always going to be a pressure or force. Let's say it doesn't have to be like facing up or facing down or sideways. That means it's pressure acting on it from all sides. So that means if you choose some kind of depth D, right, there is a force acting from the molecules from all sides like this. Okay, and you can calculate the pressure due to all those forces acting on it. So all right, so thing like this. So let's say in terms of this pressure, right, those are the molecules colliding with the wall. It could be like air molecules colliding with the wall and exerting pressure on the wall. Or you can have, let's say, thing like this is could be a water molecule, you inside the this fluid, liquid, right, and they are colliding with the wall and exerting this force. And every force acting on, let's say, this area of interest then can be considered as a pressure. Okay, so pressure per unit area. All right, so now there are two contributions to the pressure in a container of fluid, for example. One is a gravitational contribution due to the gravity pulling down on the liquid or gas, right? So if you have a container With the liquid, the gravity pulls it down. And also, if you're a gas, right, in a container, again, gravity is acting on it. There's also thermal contribution due to the collisions of the freely moving gas molecules within the walls, which depends on gas temperature. So we, in a way, have to take both of those into consideration, right? So when they collide with one another, and then when they collide with the, let's say, container wall and things like that, and there's always, you can say that's why there's always a pressure, the container walls at the bottom and everywhere, because there's constant, flow of this, molecules, and they collide with each other and things like that. All right. So another thing we can talk about here is, how the pressure varies with, let's say, altitude and also depth. So if you talk about, let's say, surface of Earth, let's say you are, here standing like this, right? So then what you have, you're basically bombarded with air molecules from all over, all around you, because those air molecules moving around you and then colliding with you. But, and in a way, like, let's say you are under all of this atmospheric weight. But you don't really feel that because you also breathe that air. So that means you have the same air inside your body and outside of your body. And then, those collisions, those pressure basically is the same from outside and from inside. That means, let's say you're in equilibrium. That means, the pressure from outside is equal to the pressure from inside. And, that's why you don't really, you don't feel compression or expansion and things like that. But pressure decreases with, with altitude. That means, for example, then if you measure the pressure on you from air molecules, then you're going to get what we call one atmospheric pressure, let's say, from air molecules. And that pressure a lot of times is known as P0, which is the atmospheric pressure. And you can write it as 1 atm as a unit for standard atmosphere. But this is also equals to 101,300 Pascal. So roughly 101,000 Pascal. So this is basically the standard atmospheric pressure. But as you go up with the, altitude, then this pressure decreases. And the reason the pressure decreases because concentration of or air molecules, right, decreases. And higher you go, less concentration, less collision with from air molecules, lower the pressure, until you get to space where technically there are no air molecules. So pressure at space, right, is zero. There is no pressure because there's no air molecules to move around and collide. All right. So in terms of then, let's say, looking at a pressure. So if you say if you hold out your arm, which has a surface area of about 200 cubic centimeters, the atmospheric pressure on the top of your arm is 2,000 newtons, or about 450 pounds. How can you even lift your arm, right? As I mentioned, right? So let's say you are being bombarded, right? There's an entire atmosphere pressing down on you, sort of like, let's say. Again, the reason is that a fluid exerts pressure forces on all directions. So not only, let's say, you have forces from above, you have forces from below, then canceling each other. Also, you have forces from inside, right? So like, let's say, all of those basically affect. So the pressure is that a fluid exerts forces on all direction, and the air underneath your arm exerts an upward force of the same magnitude, so the net force close to zero. All right, so let's look at an example here. So you have the 2 feet of a 60-kilogram person cover an area of 50 cubic centimeter. Determine the pressure exerted by the 2 feet on the ground. And if the person stands on 1 foot, what will the pressure be under that foot? All right, so one thing we can think of here is this. So let's say here's a person, and basically you have 2 feet, right? So then exerts, so let's say the term pressure goes by 2 feet on the ground, and 2 feet have a cover area of 50 square centimeter. And person is 60 kilograms, so we can find the force because the force that it exerts is equals to the weight of a person. So we can say the weight is equals to mass times gravity. So it's 60 kilograms times 9.8 meter per second square. So we can calculate this to be 588 newtons. Then we can say, all right, so then pressure is equals to force per area. So then the force is 588 newtons divided by the area, which is 500 centimeters square. But this has to be converted to meters. So we do then 100 centimeters is 1 meter, but then we have to square that, right? So then, centimeters squared at the bottom. So then we can calculate this to be roughly 11,760 Pascal, or 12, roughly, so let's say kilopascal, like that. All right, so this is part A. For part B, it says, what if it's on 1 foot? So you can take it like, let's say if it's 1 foot, then it's 250 square centimeter, let's say, covered distance, right? So, and the difference here is now you have uh, only like, let's say, the half the area. So then the pressure to, let's say, is equals to weight over area, but this is, let's say, this new area prime, right? Let's say half of the previous area, which means that 2 times weight over area. That means 2 times 12 kilopascal, so then roughly 24 kilopascal. And that will be the answer for part B, because now you have the same force acting on only half this area, so then pressure is actually doubled. All right, so then next we're going to look at in terms of how to find the pressure at some depth D. And to do this, we take a container with some liquid inside, and then we look at sort of like, let's say, how the pressure acting on the, this, let's say some kind of imaginary thing like this. So we're going to choose some imaginary cylinder of water. Again, this is actually, the water, basically part of the entire, so the water in the cylinder is part of the entire water, right? It's just sitting there. We just, imaginary choosing that small cylinder so we can use it as a sample. So then we can say that there are two, let's say surface, one at the top and one at the bottom, and the areas are the same, and it has a distance d. That means we have sort of like this cylinder where there's an area, and then there's basically it has a length d. One thing we can see here is that there's a force acting at the top, and that force is atmospheric force. Remember the equation, right? Pressure equals force over area. So then I can rewrite where force is pressure times area, right? So that means force is just a product of pressure times area. Now that means at the top, I have a atmospheric force pressing down, which is basically pressure times area. Also, what we have, this volume, this column of cylinder, this water, right, has mass. So the gravity acting at the center of mass. That means there's also the gravitational force, okay? And obviously now you have two forces acting down. So the atmospheric pressure, basically, or atmosphere pushing down, gravity pulling down. But if you look at this container with water sitting there in equilibrium, that means it has to be another force acting in an opposite direction. And that force is actually acting at this bottom surface. And you can see, right, this force is acting in the opposite direction. And this force, which is product of P times A, because again, force at the bottom, you can say it's, pressure times area, is equal to the sum of the atmospheric pressure and the gravitational force, or atmospheric force and gravitational force, because you have two downward forces, one upward force, and the system is in equilibrium. That means upward force, which is given as P times A, equal to the sum of the downward atmospheric force and the gravitational force. Okay. Now, one of the things we do here is this. So it's atmospheric pressure times area at the top, plus, so this is mass times gravity, which is the weight. So this is when I mentioned, right? So when we're going to take the mass, and we're going to always rearrange where the mass is going to be written in terms of the density times volume. But let's say here's the cylinder. What is the volume of the cylinder? Well, it's area times depth, right? Area times height, A times D. That means mass is going to be in terms of density times volume, but volume is going to be written in terms of depth times A. So then I'm going to say this plus, for the M, I'm going to replace M with density times depth times A, which is the volume, then times G. And now I can see that the area can be canceled from all the sides, right? So that means, it's end up canceling from all the sides. So then it ends up being this. Pressure at that depth D is equal to then atmospheric pressure plus this quantity known as a rho times G times D. We're actually going to call this a gauge pressure later on. Sorry. This is a gauge pressure, but this is the density of the fluid times acceleration due to gravity times D, which is the depth. So this is the pressure, right? So that you can see hydrostatic pressure at depth D. That means what we're calculating here is this. What is the pressure at this depth D? And this pressure over here is due to the pressure, or you can say, right, due to the fact that you have, let's say, all these air molecules plus all that water above it pushing it down, right? And then it's balanced by this pressure force from the bottom. That means this pressure force over here, is much stronger than pressure everywhere above it. And it actually will increase as you go lower, because you can see, right, this pressure equals atmospheric pressure plus rho G times D. As you increase D, and D is basically the depth with respect to the surface of the water. And that means, deeper you go, greater than the pressure. All right. So then what we're going to do here, we're going to look at in terms of several, let's say configurations. So for example, you have a container like this that basically has sort of like, let's say, two things connected to one another. And there's actually, here's a connection between those two containers. And the question that, can you have then different, let's say D2 or D1? Can you have different depth? Will this be possible? And the answer is no, because a connected liquid in hydrostatic equilibrium rises to the same height in all open regions of the container. Okay, because container one, container one is open, container two is open. That means, it doesn't matter which one. So, and that means the water level going to be, exactly the same. So it will rise to exactly same height if there are, let's say open containers, both of them. All right. Also, if you have two, again, open containers like this, one of the things we can do here is, for example, I use container one and I find the pressure at point one. Okay, how do I find that? Well, I find, let's say, the D1, which is the depth of point one relative to the surface. And then I can say then pressure at point one is equals to atmospheric pressure plus rho times G times D1. And I can calculate the pressure. Now, because second container has exactly same height, so then if I choose some kind of point two, and let's say D2, and I calculate the pressure at point two, so then again, atmospheric pressure plus rho times G times D2. If this is the same liquid, same density, and if D1 and D2 are the same points, then the pressure is going to be the same. And I can see that, what I have here, then P1 and P2 are the same pressure. That means if I draw a horizontal line, well, if I can do a better job at this, right? So let's say if I draw a horizontal line, I can see that those 2 points are exactly on the same horizontal line, which means that if I choose any point along that horizontal line, I'm going to get exactly same pressure. That means P3, some P4, some P5, they're all going to have the same pressure. Hydrostatic pressure is the same at all points on the horizontal line through a connected fluid. Okay, so this is important, concept, because, for example, when you go to a doctor, and let's say they have to measure the pressure, let's say at your heart, they don't wrap something around your chest. What they do, they basically wrap around your arm, because your arm is at the same level as your heart, and it's much easier to find the pressure in your arm than your heart, because it's like all you have to just wrap around your arm and find the pressure, and exactly same pressure in your heart, because it's exactly same horizontal line. All right. So sometimes the pressure, okay, right? So there, if there's external pressure in addition to the weight of the fluid itself, or if the density of the fluid is not constant, we calculate the pressure at the height y in the fluid, and the negative sign indicates that the pressure decreases with height. So this is in terms of looking at this y from the bottom of the container, and assuming this is non-uniform liquid, that means that let's say the uh, density is not constant, Then what we have to do here is then we calculate, let's say we choose some kind of sample size and say then dp dy, right? So the rate at which the pressure is changing is equals to negative rho times g. All right. And from here, what we have to do is just basically then integrate both sides, right? So first of all, let's say multiply both sides by dy, cancel this. So then we have then dp is equals to negative rho g dy, because then what we can see here is if I integrate both sides, then on this side, then I'm getting change in pressure, how the pressure changes, right? And on the right side is basically I have an integral of the rho g, and then basically rho is the, let's say, the density, but if the density is not constant, right? So g is always a constant, it can come out. Then we can have, like, let's say rho dy, depending on if the density is, changes or it doesn't change, right? And then you may be able to, let's say, then integrate over that. So, but this is kind of like, let's say, general equation. And then if needed, if, let's say, density is constant, then in a way what you have is that P2 minus P1 is equal to negative integral y1, y2. If thing like this, if this is constant density, right? So then negative rho g, then you just have dy. So this just becomes negative, rho g delta y. So just going to be simplified to this, assuming that it's constant. But if it's not constant, then you're going to have to, like, let's say, then integrate. All right, so let's look at this example here. So the surface of the water in a storage tank is 30 meters above the water faucet in the kitchen of a house. Calculate the difference in water pressure between the faucet and the surface of the water in the tank. All right, so we are given the height, which is about 30 meters. That means, or you can say, like, let's say the depth. And because water faucet and the water tank are connected, so then you can assume they're basically same liquid, right? Same fluid, same water. So, and they're also, remember, if they're connected, so then you can look at it in terms of finding, let's say, the pressure at, let's say, some point one and some point two. So let's say find, because we're asking to find the pressure difference. All right, so let's call this point one, and then right here we have then point two, which is, in your kitchen. All right, so one thing I have here is point one represents the surface of a, water tank, which is open to atmosphere. So one thing we know that P1 is equals to atmospheric pressure. So it's 1.013 times 10 to the 5 Pascal, which is roughly, 100,000 Pascal. Point two, on the other hand, is basically some height h above that point. So that means we can then calculate P2, just like the equation that we have, which is, P1, so the pressure at, point one, then plus rho g times then h. You can use d or you can h, just basically the height. But because P1, point one is the atmospheric pressure, so you can say it's P0 plus rho gh. All right, so then what I can do here is I can move this, let's say um, point one to the other side. So let's say then I have point one minus point two minus point one, which is, remember, our, what we want to do is to calculate the difference in the pressure. So then this is delta P, and this is equal to then the rho times GH. And most of the time, this is known as the gauge pressure. Okay, gauge pressure. So which is the pressure difference. So that's usually gauge pressure. So then you can say, all right, so then P2 minus P1 is equals to, the density is 1,000 kilogram per cubic meters, then 9.8, then 30 meters. So then, P2 minus P1 will be equals to 2.9 times 10 to the 5 Pascal. So that's basically our pressure difference, or the gauge pressure. Okay. All right, so here's another example. Calculate the force due to water pressure exerted on a 1 meter by 3 meter, 1 meter by 3 meter aquarium viewing window whose top edge is 1 meter below the water surface. All right. So the way we approach this thing like this. So if you want to find the pressure at one point, then we could just use this equation, right? So we learn. So P is equals to atmospheric pressure plus rho G, let's say H, let's say. But what we want to do here, we want to find the, let's say force uh, basically exerted on the aquarium viewing window. That means basically the through this entire area. Okay, which means like let's say force per area, right? So, but that means just not single point, but over the entire area. So that means we need to we're gonna need to like basically integrate for this one. All right. So the way we approach this, we choose some kind of a sample strip. So this guy over here, and we're gonna say, all right. So this is basically it has a size dy, and it is basically distance y from the top. So then we're going to need to look at in terms of this the strip that we are um, choosing. You can see, right, it has a dy as its thickness, but then its length is 3 meters because it's along the entire aquarium, right, length. So that means it has a length of 3 meters and the thickness of dy. Okay, so taking this top y equals 0, right? So then we can set up the equation for the let's say the integral for this one, right? So remember, in terms of then finding the force equation, which is force is equals to pressure times area. All right. So, but what we're going to do here is we're going to find the force for that one strip, which is basically finding the force that one strip contributes, and then this is equals to P times dA, which is its own area. And then basically I'm going to say, okay, so this is the expression for just one strip. But then I have n, let's say certain number of strips, right? That means I can break this down over, for the entire this aquarium into this many strips like that. And then, summing them up, right? Which basically becomes pretty much the integral. Now, so this is, let's say, just doing the expression for just, the force that this one strip, exerts. So P times dA. Okay. So then the pressure is, all right, so the pressure can be written as rho gy, okay? So assuming that basically it's a closed, container, so rho gy, and then dA is basically the area of that strip, which is basically its length times its width. Well, its length is L and its width is dy. That means dA is equals to L dy. So I can say it's L dy. That means that's my expression. The dF, right, is equals to rho GYL dy. And then what I'm going to do, I'm going to then integrate both sides. That means on the left side, integral of dF is just the force. And on the right side, I have integral rho gy times L and dy. And then what I'm going to do here is I'm going to say, all right, so then it's going to be then going from this, let's say the limit, right? So basically this is the closest to the surface, which is basically 1 meter, to being all the way to this distance from the surface, which is basically 2 meters. Okay, then I'm going to basically integrate with those limits. All right, so density is constant, G is constant, L is constant. All those things can come out, and then all I have here is, let's say, I can write this as y1. I can write this as y1, y2 to kind of, so you can see, right, that's y1 and y2. And then I have just basically y dy. Those are the only things I have basically that cannot be removed from the integral. All right, so it becomes rho g l y dy is just nothing but y squared over 2. Okay, and with the y1 and y2, that means what I end up here is rho g l and then y2 square minus y1 square. Okay, so then I can just plug in, 1 meter for y1, 2 meters for y2, and then just calculate by, because it's a 1,000 kilogram per cubic meters. for the density, then 9.8, then 3 meters for the L, then y2 is 2 meters square minus 1 meter square, and then calculate the force to be 44,000 newtons. And that will be the force that basically this window exert, or the force acting on that window, or the force that water molecules, right, acting an entire window, which is 44,000 newtons.